Some atoms are unstable. To become more stable, they need to give off mass, energy, or both. In that process, they may well decay and become a completely different type of atom. In this video, we're going to look at the different ways that can happen and how we can represent those different types of decay with decay equations. Nuclear radiation comes from the nuclei of atoms. So let's start off by reminding ourselves about the nucleus. The nucleus contains protons and neutrons. The atomic number or proton number tells us just how many protons are in the nucleus. The mass number tells us how many nucleons there are in the nucleus. A nucleon is a proton or a neutron, anything that lives in the nucleus. We can work out how many neutrons there are in the nucleus by taking the mass number and taking away the proton number or atomic number. The remaining number is the number of neutrons. Nuclear decay must come from the protons and neutrons in the nucleus. Let's start by looking at alpha decay. An alpha particle is made up of 2 protons and 2 neutrons. It's the same as a helium nucleus really, so we could either write it with the alpha symbol, the Greek letter alpha, or with He, the symbol for helium. It has a mass of 4 because it's got 2 protons and 2 neutrons. And it's got the atomic number 2 because it's got 2 protons. A typical example of an isotope that decays by alpha decay is uranium-238. Uranium has 92 protons, so it has the atomic number 92. When it gives off an alpha particle, it loses 2 protons and 2 neutrons. Its mass number therefore goes down by 4. Its atomic number goes down by 2, so it goes from 92 to 90. That's a different element altogether. That's thorium. The mass is now 234. We can write a balanced equation for this decay by starting off with our uranium on the left-hand side of the equation and putting our thorium on the right-hand side along with the alpha particle. There are 2 products. Notice how the mass numbers on the right-hand side of the equation add up to equal the same amount as the mass number on the left-hand side of the equation. Likewise, the atomic numbers all add up to the same as they do on the left-hand side of the equation. This is what we call a balanced equation. Here's a second example. Plutonium-239 decays into uranium by alpha decay. Complete the following equation, making sure it's balanced. Well, we're told it's alpha decay, so we can add the alpha particle. We now set about balancing the numbers. The mass number for the uranium must be 235, because 235 add 4 gives us our 239. That balances both sides of the equation. And the atomic number of uranium must be 92, because 92 plus 2 gives us 94. Again, balancing the equation. You'll always be given enough information to complete these questions. You won't be expected to learn the atomic numbers or mass numbers of certain elements, although you may be given a table where you have to look that information up. Beta decay is less intuitive. A beta particle is a high energy electron, but there are no electrons in the nucleus, I hear you say, so how can it be nuclear radiation? Well, one of the ways an unstable nucleus can try and become stable is by turning a neutron into a proton. Now, a neutron's neutrally charged and a proton is positively charged. So to balance the charges, it has to make an electron in the same process. So a neutron turns into a proton and an electron. Now, the electron goes, hey, I don't belong in the nucleus, and it flies off. That electron that flies off from the nucleus is the beta particle. Because a beta particle is an electron, it practically has no mass at all, so its mass number is 0. It does, however, have a negative charge, so we like to put a little -1 where we would normally put the proton number, just to remind us that it is negatively charged, the same relative charge as a proton, but opposite. We can therefore represent a beta particle in one of 2 ways. Firstly, using the Greek letter beta as the beta symbol, or secondly using an E for an electron. A typical example of an unstable isotope that decays by beta decay is carbon-14. Carbon has an atomic number of 6, but when it gives off a beta particle, it also gains a proton, so the atomic number becomes 7, and it's no longer carbon, it's actually nitrogen. The mass number does not change though. That's because a beta particle has such a tiny mass that the amount of mass given off is zero, really. We can write a balanced equation once again with carbon on the left hand side and the nitrogen and the beta particle on the right hand side. We check the mass numbers and make sure they balance again, and there we are, we have a total mass of 14 on both sides, and we check the atomic numbers, and once again we have a total atomic number of 6 on each side. So this is another balanced equation. Here's a different example. Molybdenum 99, and that's not easy for me to say, decays into technetium by beta decay. Complete the following balanced equation. We know that it's beta decay, so we can add the beta particle, the electron. It's now all about balancing the numbers. Balancing the mass, technetium must have a mass of 99 to make it 99 both sides. Balancing the atomic number, technetium must have an atomic number of 43, because 43 minus 1 is 42. Once again, balanced. Before I talk about gamma emission, neutron emission and beta plus decay, I'd like to steer you in the direction of my website. You can find a link in the description below. There's many free resources, including questions and worked answers to go with this video and many others. I also offer GCSE and A-level physics tuition, so if you're interested, please get in touch. You'd also be supporting me to make lots more free resources by liking, subscribing and commenting on this video. Right, nuclear gamma ray emission. This is electromagnetic radiation coming from the nucleus. It's where a nucleus gets rid of any excess energy, particularly during or just after alpha or beta decay. Because the electromagnetic radiation has no charge and no mass, then there are no equations to balance. It does not change the structure of the nucleus itself. As an example, cobalt-60 and iridium-192 are both isotopes that are used in radiotherapy. They are formed when they're bombarded with neutrons. They then have to release lots of energy, and they do this as gamma radiation, and that gamma radiation is then used to treat cancer. Before I look at neutron emission, I'm going to look at beta plus decay, and this is really aimed at those who are studying Edexcel GCSEs. If you're studying the specification of a different exam board, then you may want to skip forward a minute or so to the next chapter on neutrons. As we've already seen, beta minus decay is when a neutron turns into a proton and gives off an electron. Beta plus decay is when a proton turns into a neutron. This process gives off the antiparticle to the electron, the positron. The positron has the same mass as the electron, but most other properties are opposites because it's its antiparticle. That includes the charge, as suggested by the name, positron. The charge is positive. The atomic number therefore goes down by 1. The mass stays the same because it's only lost a proton and gained a neutron, so the mass doesn't change, and the positron mass is just about 0 as well, just like the electron. Here's an example. Magnesium-23 decays into sodium by beta plus emission. Complete the following equation, making sure it's balanced. We know it's beta plus decay, so we add the beta plus particle, the positron. It's now once again about balancing the numbers. Balancing the mass, sodium must have a mass of 23. Balancing the atomic numbers, sodium must have an atomic number of 11. Right, neutron emission. Neutron emission occurs when a nucleus is neutron rich or proton poor. It can also occur during the fission process. The emission of a neutron does not change the atomic number of a nucleus, but it does produce a different isotope. Here's an example. Beryllium-13 decays by neutron emission. Complete and balance the following equation. First, we add the decay particle, the neutron. As always, we now set about balancing the numbers. The mass of the product decreases by 1. The atomic number of the product stays the same. Because it has the same atomic number, it must be the same element, so the product must also be beryllium. So there we have it, the decay process of unstable nuclei. Alpha, which is 2 protons, 2 neutrons. Beta minus, which is an electron. Beta plus, which is a positron. We've got neutron emission, and we've got gamma rays being emitted to lose excess energy. Remember to check out the website for more resources. In the meantime, you could watch this.